Dear students, welcome to the problem solving session on Cauchy integral theorem and Cauchy integral formula part 2. In our previous videos, we learned all the basics and then we solved few problems. Before that, we saw the roadmap for problem solving. At first, we have to find the singular points from the denominator. If all the singular points are lying outside, then we have to use Cauchy integral theorem to conclude the answer as 0. If the singular points are lying inside, then we have to use Cauchy integral formula. If the singular points with higher order, for example z minus 3 whole power 4, the order is more than 1, then we have to use Cauchy integral formula for derivatives. So we see 3 problems in our part 1 video. In today's session, we are going to deal a challenging problem. Evaluate integral over c. In the numerator we have sin pi z square plus cos pi z square. In the denominator we have z minus 1 and z minus 2 dz, and the given region is mod z equal to 1 by 2. Now in this problem, denominator consists of 2 terms. Let us see how to solve this. As usual, step 1, we have to draw the figure. Mod z equal to 1 by 2. So my center is 0, 0. Radius is 1 by 2, that is 0.5. So this is my circle. Step 2, as usual, take the denominator, equate it to 0 to find the singular points. Here the singular points are 1 and 2. When I take z equal to 1, we have 1, 0. Obviously, it lies outside. Next, similarly, if you take z equal to 2, the point is 2, 0, and we see the point 2, 0 also lies outside C. So both singular points lies outside C. Next, step 3, we have to write both the singular points are lying outside C. And let us consider capital I is my question. Now we are going to concentrate on the numerator. Sin pi z square plus cos pi z square. From the basics we know z square is entire function. Similarly, both sin z and cos z also entire function. And we learn if f and g are entire function, then f of g of z, composition of f and g is also entire function. Therefore, sin pi z square is an entire function. Similarly, cos pi z square is an entire function. And sin pi z square plus cos pi z square is also an entire function. So, sin pi z square plus cos pi z square is analytic inside and on the given C. Now when we see the denominator, z minus 1 and z minus 2 are singular points, but both the singular points are lying outside. So when I take this singular point in the denominator, it will not affect the analyticity. So the whole function sin pi z square plus cos pi z square divided by z minus 1 into z minus 2 is also analytic. So I will take this as f of z. As we see in the previous video, always I take the function f of z such that it is analytic. Since my numerator is analytic and my denominator is analytic, f of z is also analytic. So f of z is analytic everywhere inside and on C. Now, according to this, capital I is equal to integral over C f of z dz, because the whole function is analytic. Therefore, we have to use Cauchy integral theorem. According to Cauchy integral theorem, if f of z is analytic everywhere inside and on C, then integral over C f of z dz is equal to 0. Therefore, my answer is 0. So we found the solution. Integral over C sin pi z square plus cos pi z square divided by z minus 1 into z minus 2 is 0. Hope you understand, students. Next, for more clarity, we are going to take the same problem, only I am changing the region. Here the region is 3 by 2, that is 1.2, and it is very important in your examinations. If they mention solve using Cauchy integral formula, then no other go, we have to solve by Cauchy integral formula. But if they say simply evaluate, you can either solve by Cauchy integral formula or Cauchy residue theorem. Choice is yours. We are going to learn problems on Cauchy residue theorem in the forthcoming videos. You feel whichever easy, you solve in that method. But if it is mentioned specifically solve by Cauchy integral formula, then you have to go by CIF. So now the region is mod z equal to 3 by 2. You know radius is 3 by 2 and the center is 0, 0. Easily we can draw the circle. Next, singular points. We have already found the singular points are 1 and 2. In this problem, at first, let us consider z equal to 1. So we get the point 1, 0. 1, 0 lies inside. Therefore, z equal to 1 is a singular point, lies inside C. Next, we take z equal to 2. Since my radius is 1.5, z equal to 2, that is 2, 0, lies outside the circle. So, one singular point lies inside. The other singular point lies outside C. As usual, step 3, consider capital I as my question. Just now in the previous problem, we see sin pi z square and cos pi z square are entire function. Therefore, sin pi z square plus cos pi z square is also an entire function. Now, when you come to the denominator, z minus 2 is a singular point, but it lies outside C. So it will not affect the problem. So I can say sin pi z square plus cos pi z square divided by z minus 2 is analytic inside and on the curve capital C. But I cannot take z minus 1 because the singular point z equal to 1 lies inside C. If you substitute z equal to 1 here, then it is not analytic. So my capital F of z is simply sin pi z square plus cos pi z square divided by z minus 2. Now we have to rewrite my question. Capital I is equal to integral over C. F of z is analytic. Always I keep f of z in the numerator. Sin pi z square plus cos pi z square divided by z minus 2. Since z minus 1 lies inside C, I am going to keep this in the denominator. So now this looks like integral over C f of z divided by z minus 1 dz. Now it is easy to catch that we can apply Cauchy integral formula to get the solution. You can see the typed version. So let us write the Cauchy integral formula as my step 4. Now compare our problem with Cauchy integral formula. Therefore, I can write capital I is equal to 2 pi I into f of 1. Next we have to find f of 1. We know that f of z is sin pi z square plus cos pi z square divided by z minus 2. Then f of 1 is simply sin pi plus cos pi divided by 1 minus 2. We know that sin pi is 0 because any sin n pi when n is integer, it is going to be 0. And cos odd pi is minus 1 and cos even pi is plus 1. Therefore, f of 1 is 0 minus 1 divided by 1 minus 2. So we get minus 1 by minus 1. It is 1. So f of 1 is 1. Now we have to substitute this in I. Our I is 2 pi I into f of 1. That is 2 pi I into 1. Therefore, the solution for my problem is 2 pi I. Hope you understand, students. In more curiosity, I am going to take the same question with different region, that is mod z equal to 3. In example 4, we took the region mod z equal to 1 by 2, and in example 5, we took the region mod z equal to 3 by 2. Now in this example 6, we took mod z equal to 3. Let us see how to deal this problem. As usual, first find the region mod z equal to 3. It is a circle with center 0, 0, radius 3. One can easily draw the figure. Already we found the singular points. 1 and 2 are singular points. Z equal to 1, that is 1, 0, lies inside C. Similarly, when you take z equal to 2, we get 2, 0. This is also lies inside C. Both singular points lies inside C. Now there comes a trouble because both the singular points lies inside C. In step 3, let us write the given question as capital I. Now we are going to deal with numerator. From the previous problem, we know that sin pi z square plus cos pi z square are analytic inside and on C. But when you take the denominator, both z minus 1 and z minus 2 lies inside C. So we cannot take that because it will spoil my analyticity. So only the numerator is analytic. I will take this as f of z. Rewriting the question, integral over C, numerator f of z, denominator z minus 1 into z minus 2 dz. Now what is the problem? I cannot apply Cauchy integral formula. The reason is Cauchy integral formula says integral over C f of z divided by z minus a into dz is 2 pi I into f of a. You should have only one singular point in the denominator, but I have two singular points in the denominator. Then how to tackle this? You have to recall your 7th, 8th standard technique. Take the denominator alone, do the partial fraction. Even we did this partial fraction in unit 3 Laplace transform. You can see the typed version. See, denominator highest power is 2 and numerator the power is 0. So I can apply partial fraction for this. We can write this as capital A by z minus 1 plus capital B by z minus 2. Very important. You should not do partial fraction by considering the numerator. It is the big error because the numerator is not a constant polynomial. Simplifying this, we get a into z minus 2 plus b into z minus 1. We can cancel the denominator. It is very simple. Let us substitute the singular points 1 and 2 to find a and b. First put z equal to 1 and then put z equal to 2. When you put z equal to 1 here, this term vanish. So we get 1 is equal to a into 1 minus 2. Therefore, capital A is equal to minus 1. Similarly, if you put z equal to 2, this term vanishes. We get 1 is equal to b into 2 minus 1. Therefore, the value of b is 1. So we found both a and b. We have to substitute here and we get this. Now we have to deal with integral over c f of z divided by z minus 1 into z minus 2 dz. It is very simple. Multiply f of z on both sides and integrating with respect to dz, we can easily achieve this. So using the partial fraction, I can rewrite this as integral over c minus 1 is there. I will write the minus here. F of z divided by z minus 1 into dz plus integral over c f of z divided by z minus 2 into dz. Now you are very confident we can apply Cauchy integral formula for this. Comparing Cauchy integral formula with our problem, we can easily write capital I is equal to minus, because in the first term we have minus 2 pi I into f of 1 plus 2 pi I into f of 2. So now our job is to find f of 1 and f of 2. Substituting here, we get the solution for capital I. We know that f of z is sin pi z square plus cos pi z square. Now substitute z equal to 1. We get sin pi plus cos pi. Sin pi is 0. Cos pi is minus 1. Therefore, f of 1 is minus 1. Next, substitute z equal to 2. Then we get sin z square is 4. So sin 4 pi. Similarly, cos 4 pi. Sin 4 pi is 0. Cos even pi is always plus 1. So we get 1. Therefore, my f of 1 is minus 1. F of 2 is plus 1. Capital I is equal to minus 2 pi I into f of 1 plus 2 pi I into f of 2. Now let us substitute f of 1 and f of 2. We get minus 2 pi I into minus 1 plus 2 pi I into plus 1. So minus into minus plus, we get 2 pi I plus 2 pi I. That is 4 pi I. Therefore, my answer is 4 pi I. Hope you understand, students. For more clarity, let us take the example 5 and 6 and we are going to compare these two in a nutshell. Z equal to 1 and 2 are the singular points. 1 lies inside and 2 lies outside, for example 5, at the region mod z equal to 3 by 2. But in the case of mod z equal to 3, both 1 and 2 lies inside C. Next, step 3, we assume the given question as capital I. Now we have to concentrate on the numerator. My numerator consists of sin pi z square plus cos pi z square. It is very clear z square is entire function, sin and cos are entire function. Therefore, sin pi z square is also entire and cos pi z square is also entire function. So we say sin pi z square plus cos pi z square is analytic everywhere. It is entire function. Sin pi z square plus cos pi z square is analytic inside and on C. Next we are going to deal with denominator. For example 5, one singular point lies inside. For example 6, both the singular points lies inside. Next we have to choose f of z. This is very much important. In this problem, numerator is analytic everywhere. So I took f of z is equal to sin pi z square plus cos pi z square. Z minus 1, z minus 2 both are singular points, but for the given region mod z equal to 3 by 2, z minus 2 lies outside and it will not affect the analyticity. So I am taking f of z as sin pi z square plus cos pi z square divided by z minus 2. But in the case of example 6, we have the region mod z equal to 3. Both 1 and 2 lies inside. So in this case, I cannot take either z minus 1 or z minus 2 because at this point the function will not be analytic. So we take the numerator alone as my f of z. Now comparing these two, I can write this as I is equal to integral over C sin pi z square plus cos pi z square divided by z minus 2. That is my f of z, and in the denominator we have z minus 1 dz. This is of the form Cauchy integral formula. By applying Cauchy integral formula, we can achieve the solution. Next, for example 6, in the denominator we have two singular points, but both lies inside C. So I cannot apply Cauchy integral theorem, as well as I cannot apply Cauchy integral formula too. The reason is, for Cauchy integral formula, there should be only one singular point in the denominator. Here we have two terms. How to split these two terms? We know we have to use partial fraction. For this, always you have to take the denominator and take the numerator as 1. And then we can easily find the constants a and b. After finding a and b, multiply this equation by f of z on both sides and integrating this equation with respect to dz, we get f of z divided by z minus 1 into z minus 2 dz is equal to integral over c a into f of z divided by z minus 1 dz plus b into f of z divided by z minus 2 dz. Now easily we can apply Cauchy integral formula twice for these two different terms and we can get the answers. Hope you understand, students. So if you have exactly one singular point lies inside and remaining all the singular point lies outside, push this to the numerator and take it as f of z. If all your singular points are lying inside, no other go. We have to use partial fractions and then we split everything into a single term. After that, we have to apply Cauchy integral formula to achieve the answer. Hope you understand, students.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.